Hello everyone, now I'm with the workshop number 7 and this workshop is about the three-dimensional CV simulation of supersonic flow over triple wedge. And usually speaking, you see the 2D version of this type of flows on the internet in the YouTube videos, but this time I'm going to give you the flavor of the 3D version with the hexa meshing done in the ICM CFD. And what I will cover is that I will cover the hexa meshing of this triple wedge because it has the 3 angles. So first step and second step, third step, I will discuss about the dimension and the angles in the coming videos, and also discuss about the dimensions in the PowerPoint slides also in the introduction of this workshop. So based on these 3 steps, we have the different type of the shock waves they are produced over these steps, and they also interact with each other. So the idea is that we need to simulate this flow, and I want to just show you that how you can make the geometry and the mesh, and then how to set up this case in the Fluent, and then most important thing is that how to post-process results and then compare with some known data in the literature, not exactly the same case, but similar case, and we need to have some idea about the solution, the similar type of the results in terms of the Mach number or the density or the static pressure difference across the shock wave. So now take a look on this workshop, and as you can see that this is the workshop in the Mastering Ansys Theory Level 1. And there are the many workshops, but now I'm numbering them with numbers like a 7. And if you take a look on the course, you can see that we have the many things here. So the one of the workshop, which is a laminar pipe flow, is going with the same name even when I'm solving them in the different softwares. But after going through the different sections, which might be counted as the workshops, separate workshops, but I just put the name as the workshop 1. So after section number 10, I guess, we have the next workshop, and here I put the name as the workshop number 2. So I can safely put the name as the workshop number 11 here instead of the 2, but anyhow. And after that, I have just recently put the workshop on the laminar pipe flow with the Fluent. And this time I'm going to put the new workshop, which is the supersonic flow over the triple wedge, and the more cases will be coming up in the next videos I will upload on the same course or maybe in the level 2 depending on the scope of each workshop. So from the slides you can see here that we have the triple wedge at the Mach number 3, and the half angle of each step is 10 degrees, 29 degrees and the 45 degrees. And the height of wedge is 3.49 and the width of the wedge is the 0.5 meters. And at the different locations, at the different steps, we have the dimension of 1.09 meters, 1.0. This is a linear dimension. On the angles, you have to calculate them, or you can directly plot them in the AutoCAD. And so we have the 1.09, 1 and 1. They are all in the meters. And the inlet static pressure is assumed to be 101325 pascals, and the inlet static temperature is assumed to be 288 Kelvin, and maybe I have put the value of the 300 Kelvin so you can change it, and it should not change the results too much because we are not talking about the numbers, we are talking about the qualitative results. Means that I want to just show you that how the results will look like in terms of Mach number, density, etc. And the operating pressure is assumed to be the 0 pascals, which is normally the case when we solve the compressible flow. And the flow is assumed to be compressible, and we will solve it as the ideal gas. So the density of air will change with temperature, and we assume that the flow is inviscid. So for supersonic flows, we can solve the case as inviscid, and we can get the very good idea about the shock waves. Definitely we will not be able to simulate the boundary layer. And for that case, you can run the case with the different types of models like the Almaras method or SST method, SST models. And the geometry file is provided as a tint file along with the domain around this wedge. And this SST stands for the shear stress transport model. And it's a combination of the K omega and the K epsilon, and it combines the best of these two turbulence models. So the main objective is that we have to look at the flow qualitatively, and you'll solve the problem in the Fluent, and we create exact meshing in the ICM CFD, and also we will use the online calculator, shock calculator, to see the Mach number after each step, and as well as the flow angle. So for example, here we have the oblique shock wave calculator, and if you put the value, let's say as a 3, and the angle as a 10, which is the case for the first step, 10 degrees here, and you can see that the result should give you the Mach number as a 2.5, and the angle should be the 27 degrees. So what I did is that I just plotted these things in the tech plot from the Fluent file. After meshing the ICM CFD, I solved the case in the Fluent, and then I took that case in the case data format or other format. I will tell you in detail. And just from here, I just exported the picture of this file, this case, in this way. And after that, I just imported that file into from here, insert and attach. And from here, I just put the one line here. So from home, let's say if I put the line here from this point, and this is a approximate method, but this should give you idea. So you can see here that the angle is 26 degrees. And while from calculator, the angle is 27.38. So it's a slightly different because our method is not accurate. And secondly, this method is analytical and our method is CFD. So again, there should be some differences in the results, and we should accept that thing. And also, if you take a look on the results, you can see that after a shock, so angle is confirmed almost, this is very less error there. And after the shock, the Mach number should be from this calculator should be equal to the 2.5. And you can see here that after the shock, the Mach number on the first step is 2.5. So we can confirm it, and also we can see there are different structures of the flow in this wave solution, and I will discuss it. And the mesh was generated in the ICM CFD, and number of nodes are 1.3 million, and you can make refinements in the wake region. And if you want to solve this case as a viscous solver, means with the turbulence model, then you can go for the more refinement in the boundary layer. And these are the solver conditions which I set for this problem, and I will discuss when I set the problem in the Fluent. And these are some results from the internet, and the flow should look like in this way, although there are the 2 steps here, and in our problem there are 3 steps. So the flow should be a similar one here. So here is the flow I have here, and here are the results where I've taken from the internet, and this is a calculator in fact, which I've shown you here. So this is all about this case. So I will first go to the ICM CFD, I will create the mesh, and after that I will solve in the Fluent, and then I take data into the tech plot, and we just make this type of plot, and then I will use the AutoCAD to measure the angle between the shock wave at the different locations. For example, for second step, I can get the angle approximately in this way. So I will just put a line here from this point and like here. So it's a 43 degrees. And you will see that although we are not getting clean flow on the second step, but the angle should be approximately near to this value. Maybe it's the 47, 48, or maybe the 14. And finally, we will discuss about this flow, how you can solve this case as a 2D case or maybe axisymmetric case. So this will be assignment for you.